Okay, today we're talking about atomic structure and the history of atomic structure and how it developed from way back in ancient Greece and how they thought about atoms to what we know about them today. So before we get into it, we got to talk a little bit about vocabulary. There's some terms we're going to use. You probably have heard them before in your other science classes, but if not, it can't hurt to go over them again. So we've got the first one we want to talk about is nucleus. So the nucleus is the small, dense region in the very center of an atom, and that's where the protons and the neutrons are. All right, a proton is a small positively charged particle. A neutron is small neutral particles. You probably could have guessed from the name. All right, and then electrons are very, very small. They're about 1,000 times smaller than a proton, and they are negatively charged. Right? And instead of being in the nucleus in the center, they are all around the outside of the atom. And then an orbital is a path that the electrons follow around the nucleus. Okay, so if you hear those terms now, you'll know what they mean, or you can look back and see. All right, so I'm going to start with just a basic idea of what we know about atoms and atomic structure today before we go back to kind of building up to that, just so you guys know what the correct version of it is. So our current understanding of atomic structure is based off of the quantum model that Schrödinger came up with in the 1920s. And it's basically a small, dense nucleus, so the protons and the neutrons in the middle, surrounded by a cloud of electrons traveling in different paths. So you can see this picture here in the middle, in there, is the nucleus, and then all these different colored blob-looking things are clouds of electrons following different paths in different orbitals. Okay, but way, way, way back when, before anyone knew any of that, the very first guy to come up with the concept of an atom was Democritus. He was an ancient Greek philosopher. He lived around 400 BC, so, 2,400 years ago. And he thought that if you cut something in half enough times, split it smaller and smaller and smaller and smaller, eventually you would get to a point where you couldn't cut it anymore. It was too small. And that little tiny indivisible piece is what he called an atom. Right, that's where the term atom comes from, because the Greek word atomos means indivisible. So he thought that every single substance had its own unique type of atom. So there would be like wood atoms and rock atoms and chicken atoms and water atoms, all kinds of different stuff. And he thought that the atoms themselves, once you got down small enough, would be little tiny solid balls, spheres. And in general, he got pretty close. His general idea was not too far off from the truth. But no one really cared. The thing about Greek philosophers back then is that it was basically a popularity contest. And this guy came along right after him, Aristotle, who you guys have probably heard of, and I assume you haven't heard of Democritus before, so Aristotle was way more popular. He disagreed with Democritus, and he supported the traditional Greek elementalism theory instead. And that was that everything is made up of 4 elements: water, air, earth, and fire, just in different ratios and different combinations. So mud would be earth and water together. Steam is water and air and fire all mixed together. All kinds of different stuff they had ideas about, but it was not in line with what Democritus thought. And that's kind of what everyone agreed on for the next 2,000 years. No one really wanted to rock the boat and disagree with these guys until the 1800s when John Dalton came along. So he was the first one to go back and look at Democritus' theory and think, maybe this guy had the right idea. So Dalton did some experiments and came up with his own atomic model. And the main tenets of his atomic model were that all elements are composed of tiny indivisible particles called atoms. So pretty much what Democritus thought. So that all atoms of the same element are identical, and atoms of any one element are different from those of any other element. So that's pretty close to true. We'll talk a little bit about why that's not exactly right on the next slide, but he had the right idea in general. And he said that atoms of different elements can combine in simple whole number ratios to form chemical compounds. And that is spot on. So he said in chemical reactions, atoms are combined, separated, or rearranged, but never changed into atoms of another element. And that's true too. Unless we're talking about nuclear chemistry, which is a very edge case, right? All other chemical reactions, the atoms themselves aren't going to change. They'll be combined into different molecules and combined with other atoms to make different compounds, but you'll still have the same number of hydrogen atoms going in as you do coming out. They're not going to change into anything different. So he was pretty on the money with that. Where he got it wrong was his second point, where he said that all atoms of the same element are identical. That's not exactly true, because there are what's called isotopes, which are atoms of the same element that have a different number of neutrons in them, which gives them a different mass. So if you look down here at this little example, these are all hydrogen. They all have one proton and one electron. That's what defines them as hydrogen. But if you look, this one has 0 neutrons. This one has 1 neutron. And this one has 2 neutrons. So they would all have different masses. They're all slightly different in terms of their behavior, but they are all still hydrogen atoms. So that's one of Dalton's main mistakes. Okay, and it took 80 years after him for someone else to come along and come up with a revision to his idea. So J.J. Thomson was the next guy to come along, and he actually discovered the electron. He discovered that there were particles smaller than the atom and that they had negative charges. He did that using what's called a cathode ray tube. And if you look here at this little video, Okay, so you can see how that was kind of a big deal, that he was able to find these little teeny tiny particles that he called them corpuscles, but today we call them electrons. And his explanation was that these must be particles that are inside the atom. So his model, he ended up calling it the plum pudding model, or the chocolate chip model, is what I like to call it, because no one really knows what, like, I've never seen a plum pudding in my life. But what his model is that the atom is a big solid sphere of positive charge that has these little tiny small chunks of negative charge embedded in it and scattered all throughout it. So it's like a chocolate chip cookie with the chocolate chips. So that was the model that was accepted for the next 30 years or so, until the next guy came along. And Rutherford was actually one of Thomson's students. So he learned from J.J. Thomson, and he thought, well, I don't know, I think there might be some flaws in his idea. So he came up with his own experiment to try and prove Thomson wrong. So what he did was he set up a thin sheet of gold foil. And what's really interesting about gold and a couple other metals is that when you spread them out into foil, you can spread them out very, very thin, to where they're only 1 or 2 atoms thick of a piece of foil. So he did that, and he set up a little sheet of foil, and then he fired protons at it. Alpha particles is what they're called, but they're just protons. And most of those particles passed straight through it. Now, if J.J. Thomson's model was correct, and the atoms were these big round spheres of positive charge, firing a positive charge at them, they would repel each other, right? Positive charges repel positive charges. It's like if you try and put 2 positive ends of a magnet together, they don't want to stick. So if you're firing positive charges at these big positive spheres, it's going to send them back, or shoot them off to the side, or deflect them. But what happened was, most of the particles he fired went straight through and didn't even slow down. Now, some of them were deflected off to the sides, and some bounced straight back, but the majority of them went right through. So Rutherford kind of thought about it for a minute and decided that the only way that made sense is if most of the atom was just empty space, and that there was a very small, dense center area that contained all of the positive charge. So he called that center area the nucleus, and everything else around it, he thought all the negative charges were kind of just scattered around it, out in empty space. So here we've got another quick little video explaining the gold foil experiment. So we'll watch this real quick, and I'll walk you through it. So here he's got the alpha particle. This is what's creating the protons that are shooting out. And then here on the far end is the gold foil that he's shooting them through. So they go through this little slit here this is called the deflection screen. It's what's going to record where the particles land. So yeah, blah, blah, blah. The alpha particle emitter shoots them out. They get filtered down by these 2 things to where they're coming in one at a time, and they go through that little slit, and then they hit the gold foil. And as they hit, you can see that most of them are coming out relatively unscathed, straight out the back. Some are deflected up or down a little bit. This one and a couple others go back towards the front. But for the most part, they go almost straight through. And the reason that is, if we get this zoomed in view, you've got this central positively charged sphere in the middle that's deflecting them just barely as they go through all the outside stuff. But if they get too close to it, every now and then it'll deflect them at a sharper angle or bounce them straight back. All right, so that was his proof of his model. All right, about 10 or so years later, Niels Bohr came along, and he was, he agreed for the most part with Rutherford, but his big improvement was that the electrons aren't just randomly scattered around on the outside. They travel in distinct orbitals, distinct energy levels away from the nucleus. So he said that if you add more energy to an atom, the electrons can move up or down an orbital if you take that energy back away. But that they would always be a set distance away. They would either be here or here, but there's not going to be any electrons in this in-between zone. And that's referred to as them being quantized. All right, Bohr's model, this is what you probably think of when you think of an atom. It's the one that, for most intents and purposes, we will use in our class because it's good enough. But there is one step further that it gets taken by Schrödinger and Heisenberg in the 1920s as well. So what they found is that the electrons didn't actually follow these orbitals in straight lines like Bohr thought they did. He thought they orbited around them like planets orbit the sun in a relatively straight line. What Schrödinger and Heisenberg found was that the electrons acted more like waves than particles. They were going all over the place, basically, but within set regions. And what they found out was the more they studied them, they found that it was impossible to predict where an electron would be, really, other than saying it's somewhere in this region, somewhere in this cloud area, but we don't know exactly where. So that's what you're seeing here, is that all of these colorful shapes are regions where the electrons could be somewhere within there at any given time, rather than these very distinct orbitals that Niels Bohr proposed. And this is, generally speaking, the most correct model of an atom that we have nowadays, but it's sometimes more complex than it's worth to think about. And so a lot of times we will use the Bohr model just because it's close enough. All right, so that is atomic structure and the history of it, the scientists behind it. So you'll have a little homework assignment on this, and then you'll have one more lesson today, and then you're good.